Hello dear students, welcome you all. How is everyone? So let us start today's class. So we are discussing lecture number 3 of strength of materials. Okay, so ESE engineering services previous year's questions we are discussing, and in this 2 lectures are already completed. This is the third lecture we are going to start today. Okay, so first chapter is going on, so all the questions of first chapter. So in this lecture we will be discussing ESE prelims questions of years 2007 to 2014. Okay, these 7 years questions, 8 year question basically we'll be discussing in today's class. Okay, so let us start. First question: what is the correct sequence of the following metals in the decreasing order of their Poisson's ratio? Okay, so decreasing order of their Poisson's ratio. First let us see what is the Poisson's ratio of aluminium. So Poisson's ratio of aluminium is 0.33. Cast iron Poisson's ratio is 0.1 to 0.2. Steel's Poisson's ratio is 0.25 to 0.33. Okay, now cast iron's Poisson's ratio is something about 0.2 to 0.27, something in this range. Okay, so decreasing order, highest Poisson's ratio is of aluminium, then we'll have steel, and then we'll have cast iron. Okay, so steel is 3 and cast iron is 2. Okay, so 132 is the correct answer. Option C is the correct answer. Okay, clear. Next question, question number 2. A steel rod 100 mm long is held between two rigid supports. It is heated by 20 degrees Celsius. If the coefficient of thermal expansion of the material of the rod is 15 into 10 to the power minus 6 per degree Celsius, and the modulus of elasticity is 200 into 10 to the power 3 meganewton per meter square, what is the stress in the rod? So will you try this question? Do you want to try this question yourself? Okay, so let me solve this question. So steel rod 100 mm long is held between two rigid supports. So we are having a steel rod. Okay, so length of the steel rod is 100 mm and this is held between two rigid supports. It is heated by 20 degrees Celsius. So that means rise of temperature is 20 degrees Celsius. So temperature increase is 20 degree Celsius. Okay, so if the coefficient of thermal expansion of the material is 15 into 10 to the power minus 6, so alpha is equal to 15 into 10 to the power minus 6 per degree Celsius, and modulus of elasticity E is given as 200 into 10 to the power 3 meganewton per meter square. What is the stress in the rod? Okay, so you know the formula of stress. Stress will be equal to alpha TE. Okay, so alpha is given as 15 into 10 to the power minus 6. 15 into 10 to the power minus 6. Temperature rise is 20 degrees Celsius. 20 into E, Young's modulus is 200 into 10 to the power 3. 200 into 10 to the power 3. Okay, so 15 into 20 into 10 to the power 3. Let us see. So 2 zeros here, 3 zeros here, 5 and 6 zeros. So 10 to the power minus 6, and all these zeros will cancel out. Okay, we will be getting 15 into 2, that means 60 meganewton per meter square. 60 meganewton per meter square will be the correct answer. So we'll be getting option C as the correct answer. Okay, option C is the correct answer, right? Let's move on to next question. Next question: if modulus of elasticity of a material is 189.8 giganewton per meter square, so Young's modulus of elasticity E is given as 189.8 giganewton per meter square, and its Poisson's ratio is 0.3. So mu is 0.3. What is the approximate value of shear modulus of the material? Okay, so we have to find out the shear modulus. What is the formula of shear modulus? So relationship between elastic constants is very important. E is equal to 2G 1 plus mu. This is the relationship. So if we are given E and mu, we have to find out G. So G will be equal to E upon 2 1 plus mu What is the value of E? E is 189.8 divided by 2 into 1 plus mu. That means 1 plus 0.3. So it will be 189.8 divided by 2.6. 189.8 divided by 2.6. Okay. 189.8 divided by 2.6. Almost one third. So one third of 150. One third of 180 is 60. One third of 180 is 60. This is little bit more than 0.6, 1.3, 2.6. Okay. So 2 into, so 189.8 divided by 2.6, 73. Exactly 73 is coming. So approximately we can find out one third of 180 is 60. Okay. So let it is little bit less. And it is the denominator is little bit less than 3 and this is little bit greater than 3. So approximately we will get 73. Means just by approximation. Okay. Now exact calculation is coming 73. Okay. Now in a body loaded under plane stress conditions, what is the number of independent stress components? Okay. So number of independent stress components. In order to completely specify the state of stress at a point. Okay. So in plane stress condition, how many total number of stress components are required? In plane stress condition, total number of stress components are required. This is sigma x, sigma y. Okay. This is tau xy. Okay. This is tau yx. Tau yx. Okay, so these are the stress components that are required, but we know tau yx and tau xy, they are equal to each other. They are equal. So independent stress components required are sigma x, sigma y and tau xy. So we need 3 independent stress components. 3 independent stress components are required. That means correct answer is option A. Clear? Let's move on to next question. The value of modulus of elasticity for a material is 200 giganewton per meter square. So E is given as 200 giganewton per meter square. Okay. Options are also given in giganewton per meter square, so no need to change the units. Okay. Poisson's ratio is given as 0.25, so mu is 0.25. What is the modulus of rigidity? So again, relationship between elastic constants. So modulus of rigidity G will be equal to E upon 2 1 plus mu. What is the value of E? E is 200, okay, divided by 2 into 1 plus 0.25. So that means this is 1.25. 1.25 into 2 will be 2.5. So 200 divided by 2.5. 100 divided by 2.5 will be 40 and this will be 80. So we will be getting 80 giganewton per meter square. 80 giganewton per meter square. Correct answer will be option D. Clear? Are you able to understand? Any doubt? If you face any doubt in any question, you can ask straight away. Okay. So this question, I think it is clear. Let's move on to the next question. So next question, a stepped column carries loads as shown below. Okay. So there are 2 loads acting here, P load and here P load. 2 loads are acting in the stepped column. What is the maximum normal stress in the column at B? So we have to calculate maximum stress in the column at B. So at B, there is junction between 2 columns. 2 cross sections can be possible at B. This smaller column, smaller diameter and larger. Okay. So at B in the larger diameter column. So we have to find out the stress here. So when we are calculating the stress here, stress will be equal to what? Force upon area. Now total force will be this P and this P, both will get added. Okay. So total force will be, let us write force divided by cross section area. Okay. So force will be 2P here, 2P, and area will be, it is given 1.5A. So 1.5A. So very simple, 2P divided by 1.5A, correct answer will be option C. This will be the stress, right? Let's move on to next question. I hope this is clear. Next question, a composite system where the components are of equal lengths is subjected to temperature rise. So we are having a composite system. Composite system means there are two materials bonded together, two different materials are bonded together. Okay, so these are the two different materials, these are bonded together. This is the composite system. It is subjected to temperature rise. So if we increase the temperature, which one of the following stress will be developed in the component having highest coefficient of linear expansion? Okay, so if alpha is greater, stress, if alpha is greater, it will want to undergo higher increase in length, but the other material will be increasing less, so it will be pulling it. Okay, so the material with higher alpha, will undergo compressive stress. Okay, so material with higher alpha will undergo compressive stress if we are increasing the temperature rise. In temperature rise, material with higher alpha will be subjected to compressive stress and material with lower alpha will be subjected to tensile stress, right? Next question. What is the nature of stress in a ceiling fan rod? Okay, so we are having this ceiling fan rod and here is the ceiling fan. Okay, so this is the ceiling fan. This is the ceiling fan, okay, hanging. So the weight of the ceiling fan is acting downward. So if I draw the free body diagram of this, okay, so let us say weight of ceiling fan is W, it is pulling it downward, and the ceiling is applying equal and opposite force like this, W, okay, so it will be subjected to tensile stress. Okay, so nature of stress will be tensile here, tensile. So it will be, ceiling fan rod will be subjected to tensile stress, right? Let's move on to next question. Some structural member subjected to long time sustained loads deform progressively. Progressively means the deformation is keeping on increasing with time. Okay, so some structural member subjected to long time sustained loading deform progressively with the time, especially at elevated temperature, especially at high temperature. What is such a phenomenon called? So this phenomenon is called as creep. Okay, okay, clear. Next question. The compounded bar consists of material A encased in material B. Okay, so we are having a compound bar similar to what we have seen earlier. So this is the compound bar. One material is encased inside another material like this. It is tightly secured at the ends. So at the ends there is no differential movement. Okay, whatever elongation will be there, they both will elongate or compress by the same amount only. Okay, so it is tightly secured at the ends. Coefficient of thermal expansion of A is more than that of B. So alpha A is more than alpha B if the temperature of the bar is increased. So if the temperature of this entire bar, entire assembly is increased, what will happen? The stresses induced will be, so the material which is having higher coefficient of thermal expansion, it will undergo compression, it will be having compressive stresses. Okay, so it will be subjected to compressive stresses, and the material with lower alpha, lower thermal expansion, will be subjected to tensile stresses. Okay, so tensile in both the materials wrong, compressive in both the materials wrong. Tensile in material B, yes, tensile in material B and compressive in material A. Correct answer will be option C. Option C will be the correct answer. Is it clear? Next question. Assertion. In a tension test on a cast iron specimen, so cast iron specimen, cast iron is which type of material? Cast iron. Cast iron is brittle material. So this is the case of when brittle material is subjected to tension loading. So when brittle material, the failure of specimen is on a cross section perpendicular to the axis of specimen. Okay, so brittle material is weakest in what? Brittle material is weakest in tension, and cross section which is perpendicular here, it is subjected to tension. Okay, tension test is there, so cross section perpendicular to the axis of the specimen, this is subjected to tension only, and brittle material is weakest in tension, so the failure will be along this plane only. Okay, so this will be, assertion will be true or false? Assertion will be true or false? Assertion is true. Okay, now reason, the failure of the specimen is on a plane subjected to maximum tensile stress, correct? Okay, it is subjected to maximum tensile stress, and cast iron is relatively weak in tension. This is also true, and this is the correct explanation, right? So both the statements are true. Assertion is also correct, reason is also correct, and R is the correct explanation of A. So option A will be correct answer. Is it clear? Okay, next question. I hope it is clear. Let's move on to next question. Again, assertion and reason question. In a tension test on a mild steel specimen. Now, mild steel is which type of material? Mild steel is ductile material. So if I see mild steel, ductile material is weakest in shear. So it will fail in shear. Okay. So in a tension test on a mild steel specimen, the failure of specimen is along a plane at 45 degree to the cross section. Yes, this is correct. So if I apply tension, mild steel will be subjected to tension loading only, but at the 45 degree angle, it will be subjected to shear. Okay, so maximum shear will be at 45 degree and failure will be along that plane only. So this is true. True. Reason, the failure of the specimen is on a plane subjected to maximum shear stress. Yes, this is also correct. So failure of the plane is on a plane subjected to maximum shear stress because ductile material, it is weakest in shear, and failure plane, the maximum shear plane is at 45 degree. Okay, so maximum shear stress and mild steel is relatively weak in shear. This is also true. So both the statements are correct, and the reason is explaining the assertion. Okay, so correct answer will be both A and R are true, and R is correct explanation of A. So option A is the correct answer. Let's move on to next question. I hope this is clear. If there is any doubt, you can ask anytime. Next, a square steel bar of 50 mm side and 5 meter long is subjected to a load whereupon it absorbs a strain energy of 100 joules. Okay, so we are having a square steel bar of 50 mm side. Square steel bar. Okay, so 50 mm side and 5 meter long. So that means this is the cross section is 50 mm. Just a minute. Okay, so the cross section is 50 mm. So bar is something like this. This is 50 mm. So cross section is 50 mm by 50 mm. Okay, and the length is 5 meter. That means 5000 mm. Okay, now it absorbs a strain energy of 100 joule. What is the modulus of resilience? Okay, so if we want to calculate modulus of resilience will be strain energy per unit volume. Strain energy per unit volume. Okay, so strain energy is given 100 joules. Okay, 100 joules means 100 Newton meter. So strain energy is 100 Newton meter. So let us convert that meter into mm. So 1000 mm. Okay, this is the strain energy stored. It is already given in the question, 100 joules. 100 joules means Newton meter. Okay, so we have converted that Newton meter into Newton mm. Now volume will be how much? 50 into 50 into 5000. 50 into 50 into 5000 mm cube. Okay, so the units will be Newton mm per mm cube, Newton mm per mm cube. So this is B, option B wrong, and option D is also wrong. Okay, now 3 zeros cancelled from here. These are cancelled. 1 0 from here, 1 0 from here. It is coming 1 by 555. So 1 by 125. 1 by 125 Newton mm per mm cube. So correct answer will be 1 by 125 Newton mm per mm cube. Correct answer will be option A. Clear? Okay, so let's move on to next question. A solid metal bar of uniform sectional area throughout its length hang vertically from its upper end. Okay, so there is a bar, prismatic bar. Uniform sectional area means prismatic bar. Okay, and it is subjected like this vertically from its upper end. So at upper end it is fixed and it is subjected vertically like this. Details of the bar are, so length is given as 6 meter. 6 meter is the length of the bar. Material density rho is equal to, density means it is given in Newton per mm cube. Okay, so it is given as weight density. So 8 into 10 to the power minus 5 Newton per mm cube. Young's modulus is also given 2 into 10 to the power 5. So E is equal to 2 into 10 to the power 5 Newton per mm square. What will be the total elongation of the bar in mm? So if I want to calculate the total elongation, do you know the formula for this? Do you know the formula? This is the elongation will be due to self weight. So elongation due to self weight, delta will be equal to rho L cube rho L square upon 2E. Okay. Now if I put rho 8 into 10 to the power minus 5 into length, what is the length? 6 meter. So 6000 mm whole square divided by 2 into Young's modulus. What is the value of Young's modulus? Young's modulus is 2 into 10 to the power 5, 2 into 10 to the power 5 Newton per mm square. So this will be equal to, how much we are getting? Just a minute, let us calculate. So we are getting 8 into 10 to the power minus 5 into 6000 square whole upon 2 into 10 to the power 5. We are getting we are getting 72 by 10 to the power 4. We will be getting 72 by 10 to the power 4 Newton per mm square. Yes, 72 by 10 to the power 4. Sorry, not Newton per mm square. We will be getting in mm. Okay. Now here this will be rho only. This will be rho only. Okay. If you see the unit, if you match the unit, okay, this is Newton per mm cube. Okay, this is Newton per mm cube. This is mm square. So Newton per mm cube into mm square. Okay, divided by E, Young's modulus, Newton per mm square. Newton per mm square. So if I cancel out these two, what I am getting? I am getting mm here. Okay, so 1 mm and mm square. 1 mm will be cancelled out, the remaining will be in mm. Okay, so like this, by unit we can also solve. Okay, so let's move on to next question. A circular rod of diameter 30 mm, and length 200 mm is subjected to a tensile force. So we are having a circular rod, diameter is 30 mm, okay, length is 200 mm, is subjected to tensile force. So how much tensile force, that we don't know. Okay, what we are given? Extension of the rod is 0.09 mm. That means change in length is given as 0.09 mm, and the change in diameter 0.0045 mm. What is the Poisson's ratio? So if I want to calculate Poisson's ratio, I will be getting lateral strain means diametric strain divided by longitudinal strain. Okay, so diametric strain will be delta D by D, and longitudinal strain will be delta L by L. So I can write it down as, delta D by D into L by delta L. Okay, so this will be the Poisson's ratio. So let us calculate Poisson's ratio. Poisson's ratio will be equal to delta D. What is change in diameter? 0.0045 divided by D, original diameter 30 mm. 30 mm is the original diameter. Then length. So I have to multiply length. Length is 200 mm divided by original length. Original length is there. Change in length. Change in length is given as 0.0045. 0.09. Okay, so if we solve this, 200 into 0.0045, I'll be getting 0.9 divided by 30 into 0.09. Okay, so 30 into 0.09 I can write as 3 into 0.9. 3 into 0.9. So 0.9 and 0.9 will be cancelled out. I'll be getting 0.3. Oh, sorry, 1 by 3. So Poisson's ratio will be 1 by 3, and that will be equal to 0.33. So correct answer will be option C, 0.33. Option C, 0.33 will be the correct answer. Okay, let's move on to next question. For a material having modulus of elasticity equal to 208 gigapascal. So modulus of elasticity, that means Young's modulus is given as 208 gigapascal. Now E here given as, it is given in gigapascal, options are also given in gigapascal, so no need to change. Poisson's ratio is equal to 0.3, so mu is 0.3. What is the modulus of rigidity? So modulus of rigidity, again based on this single formula, so many questions have been asked. Okay, so modulus of rigidity is how much? It will be equal to E upon 2 1 plus mu. This is the modulus of rigidity, or we also call it as shear modulus. This is also called as shear modulus. Now Young's modulus is 208 gigapascal divided by 2 into 1 plus mu. 1 plus mu means 1.3. 1 plus 0.3, 1.3. So 104 by 1.3. 104 by 1.3. How much approximately? 104 by 1.3. This cannot be there, this cannot be there. So it will be either 74 or 80. So that we have to now calculate. So 104 divided by 1.3, 80 is the correct answer. Correct answer is option B, 80 gigapascal. Okay, let's move on to next question. 80 gigapascal. Next question on your screen, given E as the Young's modulus of elasticity of material, what can be minimum value of its bulk modulus of elasticity? So we have to see the relationship between E and K. So E is equal to 3K 1 minus 2 mu. E is equal to 3K 1 minus 2 mu. So K, minimum value of K we have to find out. Okay, so minimum value of K. K will be E upon 3 1 minus 2 mu. Now here if you see, E is given as constant. Okay, now minimum value of K will come when denominator is maximum. Okay, K will be minimum when denominator is maximum. And when will denominator be maximum? When this value, negative value, minus value, this is minimum. Okay, so when will this become minimum? So 1 minus 2 mu is maximum. When 1 minus 2 mu is maximum, then only we can get minimum value of K. So when will 1 minus 2 mu become maximum? 1 minus 2 mu will become maximum when this value equals to 1. When this value becomes equal to 1. Okay, so when mu equal to 0. When mu is equal to 0, then we will be getting 1 minus 2 mu as maximum. Okay, so for minimum K, 1 minus 2 mu is equal to 1. This will be maximum. Okay, so K is equal to how much? K will be how much? Now this 1 minus 2 mu has become equal to 1. So K will be equal to E by 3. Okay, so this will be the minimum value of K. Minimum value of K. So what is the minimum value? E by 3. Correct answer is option B. Is it clear? Next question. Mild steel bar of square cross section 25 mm into 25 mm is 1 meter long. Okay. It is subjected to biaxial stress sigma x is equal to 480 Newton per mm square in tension and sigma y is equal to 400 Newton per mm square in compression. E is equal to 2 into 10 to the power 5. Mu is 0.3. What is the elongation of the bar in mm in x direction? So before we calculate elongation in x direction, let us calculate strain in x direction. Okay. So by using generalized Hooke's law, we'll be calculating strain in x direction. So what will be the value of strain in x direction? It will be equal to stress in x direction by E minus mu stress in y direction by E minus mu stress in z direction by E. Okay, so here only x direction and y direction are given. Okay, stress in x direction is given, stress in y direction is given. We are not given stress in z direction. That means stress in z direction will be 0. So this part will become 0. Now sigma x is given as 480 Newton per mm square. So let us write 480 here minus mu Poisson's ratio is 0.3 into sigma y is 400 Newton per mm square, but this 400 Newton per mm square is compressive, so we'll write minus 400 Newton per mm square whole upon Young's modulus. What is the value of Young's modulus? 2 into 10 to the power 5. 2 into 10 to the power 5. Okay. Now 480 minus 0.3 into 400. 480 plus minus minus will be cancelled out. Okay, so we'll be getting 480 plus 0.3 into 400, we'll be getting 600. So this value will be 600 divided by 2 into 10 to the power 5. Okay, so this is the value of strain in x direction. If I want to find out the change in length in x direction, I'll multiply this with original length. Strain in x into original length of x direction. So strain in x is 600 divided by 2 into 10 to the power 5 into what is the original length? 1 meter long. Okay, 1 meter long. This is the original length, 1 meter. 1 meter means 1000 mm. So we'll be getting, okay, in mm we have to find out. So 600 into 1000, how many zeros are there? 1, 2, 3, 4, 5. 5 zeros and 5 zeros cancel out. 6 by 2. That means we'll be getting 3 mm. Correct answer will be 3 mm. 3 mm is the elongation. So correct answer will be 3.0. That means D option is the correct answer. Okay. Let's move on to the next question. A mild steel rod tapers uniformly from 30 mm diameter to 12 mm diameter. Okay. Mild steel rod tapers uniformly from 30 mm diameter to 12 mm diameter. 30 mm diameter to 12 mm diameter. Okay, so this is the tapering. The rod is subjected to an axial load of 12 kilonewton. So we have applied axial load of 12 kilonewton. Okay, 12 kilonewton. E is equal to 2 into 10 to the power 5 Newton per mm square. What is the extension of the rod in mm? So extension of the rod, what is the formula? 4 PL upon pi D1 D2 E. Okay, so this is the formula. Length is given. Yes, length is given as 300 mm. So we should also mention this 300 mm is the length. Okay, so this will be required. So 4 into P, 12. What is the force? Force is given as 12 kilonewton. So force is 12 kilonewton. So 12 into 10 to the power 3 into length. What is the length? 300 mm is the length. 300 mm is the length divided by pi. What is the value of diameter? Diameter D1 and D2, 12 and 30. 12 into 30 are the diameter, and Young's modulus is 2 into 10 to the power 5. 2 into 10 to the power 5. Now if we see here, all the values are given such that their maximum values are cancelling out with each other. So 12 will cancel out with 12, 30 will cancel out with 300, we will be left with 10 here. Okay, then what we will be left with? First of all, let us see how many zeros are there. So in the numerator we are having 4 zeros, and in the denominator we are having 5 zeros. So 1 zero will be remaining in the denominator. So whatever is there into this. Okay, now 4 divided by 2 pi. 4 divided by 2 pi, that means 2 upon pi into 10. Okay, so 2 upon pi we will be getting 1 upon 5 pi. 1 upon 5 pi. 1 upon 5 pi is the correct answer. That means option D is the correct. We are getting 1 upon 5 pi. Clear? Now let's move on to next question. Poisson's ratio is defined as the ratio of, very easy question. Very easy question in ESE 2009. Poisson's ratio is defined as the ratio of longitudinal stress and longitudinal strain, lateral strain and longitudinal strain. So correct answer will be option B. This laddu, everyone will eat it. Okay. Next question. 2010. Now we are coming to 2010, and this is the problem of indeterminate structure. Okay, so we have to apply a compatibility condition also, but it is very easy. Okay, so prismatic bar ABC is subjected to an axial load of 25 kilonewton. So at the junction, at the point B, 25 kilonewton load is applied like this, and both the ends are fixed. Okay, end A and end C are supported. Okay, fixed support. This length is given as 2L, this length is given as 3L. So should I solve this by long method or short trick method? Tell me. Let us first solve it by short trick method, and then if you say, sir, solve it by long method also, then I will solve with long method. So what is the short trick? Short method is that here we'll be having RA in this direction. See, if I have applied load in this direction, then support reactions will be in opposite direction. Okay, so RA will be in this direction and RC will be in this direction. Both support reactions will be in this direction. So external forces like this, support reactions will be opposite to that. Okay, so RA and RC are like this. Now if this is plus 25 kilonewton, so this will be minus, this will be minus, so both will be minus, so both will be minus, so this option is gone and this option is also gone. Yes. Now what will be the value of RA? RA will be whatever load is there, load into opposite length divided by total length. Okay, whatever is the applied load, so applied load into opposite length divided by total length. This will be the value of support reaction. Okay, so what is the value of load? Load is 25 kilonewton into what is the opposite length? 3L. Total length is 5L. Okay, so 5 3s are 15, so we'll be getting 15 kilonewton. RA is 15 kilonewton. RB will be 10 kilonewton. Okay, 15 plus 10 will be 25. So RA will be P minus RA. P is how much? 25 minus 15, it will be 10 kilonewton. Okay, so RA is 15 minus 15 and RC is not RB, it will be RC. RC will be minus 10 kilonewton. Okay, so both will be negative sign. Okay, this we have calculated only magnitude. So this is the short trick. I hope short trick is clear to you. So in objective question, no need for the long method. Okay, in long method what we will do, first we will use equilibrium equation, that this load will be equal to RA plus RC. Okay, summation Fx equal to 0. From that we will be getting external load will be equal to RA plus RC. Okay, then compatibility condition will be change in length of this part plus change in length of this part will be equal to 0. So change in length of both the parts, we will add them together and it will be equal to 0 because these supports are fixed, right? Let's move on to next question. Next question, very easy question. Consider the following salient points in a stress strain curve of a mild steel bar. Okay, so these are the points: yield point, breaking point, yield plateau, proportionality limit, ultimate point. The correct sequence in which they occur. So we have to find out the correct sequence. So let us see what is the correct sequence. So if I draw stress strain curve of a mild steel bar, stress strain curve is something like this. This is my stress strain curve of mild steel bar. Okay, so from yield point, breaking point, yield plateau, proportionality limit, ultimate point. First I will be getting proportionality limit. Okay, so something here I will be getting proportionality limit, fourth point, proportionality limit. Okay, it is here. Then here we will be getting yield point. This is yield point 1. Okay, and this entire plateau, this region is yield plateau 3. Okay, so 4 1 3. Now breaking point and ultimate point. This is ultimate point here 5, and this is breaking point. Breaking point is where? 2. Okay, so 4 1 3 5 2. 4 1 3 5 2. This is the correct sequence. Okay, clear? So 4 1 3 5 and 2. This is the correct sequence. Okay, so option C is the correct answer. Option C is the correct answer. Clear? Let's move on to next question. Next question, a material in which large deformation is possible before absolute failure by rupture takes place. So just take the example of mild steel only. Here, before the fracture, large deformation is happening, and at this point, ultimately, finally, we are getting the rupture or failure or breaking point. So this will be called as rupture point or failure point or breaking point. Okay. So before rupture, there is large deformation. Okay. So this type of material is called as ductile material. So correct answer is option A. Option A is the correct answer. Clear? Next question, assertion. A material is incompressible if its Poisson's ratio is 0.5. What do we mean by incompressible? When a material is incompressible, here it means that the volume is not changing. Okay, some people might think that incompressible means if I applied load, it will not compress at all. No, here it means that material is incompressible when volume is not changing. Okay, so is it true? So when volumetric strain will be sigma x plus sigma y plus sigma z, okay, upon E into 1 minus 2 mu. This is volumetric strain. Okay. Now, if Poisson's ratio is 0.5, that means mu is 0.5. If I put mu as 0.5 here, I'll be getting 1 minus 2 mu as 0. When 1 minus 2 mu is 0, that means my volumetric strain is 0. When my volumetric strain is 0, that means change in volume is also 0. Okay. So if I put mu is equal to 0.5, this entire term will become 0. And when this entire term is becoming 0, then this will become 0. And when this is becoming 0, then change in volume is 0. And when change in volume is 0, my material is incompressible. Okay. So assertion is correct. True. Next, the bulk modulus K is related to modulus of elasticity and Poisson's ratio as per well-known relationship. So bulk modulus K is related to Poisson's ratio and Young's modulus by a well-known relationship. This is the relationship. This is also true. This is also true. Okay. Now, both are individually true. But is this correct explanation of this? Is this correct explanation of this? Bulk modulus is what? Bulk modulus is all-round stress divided by volumetric strain. Okay. Now, if on applying pressure, volumetric strain has to be 0, that means bulk modulus has to be infinite. Okay. And when this 1 minus 2 mu, again, if I put mu is equal to 0.5, this will become 0 and my bulk modulus will become infinite. My bulk modulus will become infinite. And when my bulk modulus is becoming infinite, that means my material is very strong. Okay. And there is no volumetric strain. Okay. So this is explaining this or not? It is correct explanation or not? They are related by well-known relationship. Okay, this much only is given. Okay, so we can say that if we dig deep into this, then we can say that yes, they are related. But just stating this, they are not. It is not explaining it. Okay, so we can safely mark it as B option. B is the correct answer. Okay, clear. Let's move on to the next question. ESC 2012. If a material has identical elastic properties in all the direction, it is said to be. So very easy question. Isotropic. Okay. Identical properties in all direction. Identical properties in all directions. Orthotropic means properties change, different properties at 90-degree angle. Okay, at property change at 90-degree. Okay, homogeneous means same properties throughout volume. Same properties throughout volume. Throughout volume. And elastic means recovered after removing recovered after removing stress. Okay, so that means identical properties in all the direction, isotropic material. Correct answer is option B. Okay, next question. Two circular mild steel bars A and B of equal lengths L have diameters 2 centimeter and 3 centimeter. Two circular mild steel bars A and B. Okay, so this is diameter A and this is B. Okay, diameter A and B, 2 centimeter and 3 centimeter, each is subjected to tensile load of magnitude P. Ratio of elongations, okay, length is same. Okay, so this is diameter 2, this is diameter 3. Okay, they are subjected to tensile load of P. Okay, so same load is applied, ratio of elongations is asked. Okay, so delta A upon delta B will be equal to P L upon A1 E upon PL upon A2 E. Okay, so that means elongation is inversely proportional to the area. So delta A upon delta B will be delta A upon delta B will be equal to A2 upon A1, A2 upon A1. That means it will be equal to diameter of diameter of B square divided by diameter of A square. Okay, so cross-sectional area will be pi by 4 d square. So pi by 4 and pi by 4 will be cancelled out. Diameter square divided by diameter square. Okay, so diameter of B, change in length of A upon change in length of B will be equal to diameter of B, how much? 3. So 3 square divided by 2 square. So it will be 9 by 4. Correct answer will be option D. 9 by 4 is the correct answer. Okay, next question. A mild steel rod tapers uniformly from 24 mm diameter. So D1 is equal to 24 mm diameter. D2 is equal to 12 mm diameter over its length of 400 mm. Okay, so this is the length given. The rod, when held vertical, is subjected to an axial tensile load of 12 kilonewton. E is given. Extension of the rod in mm. Now in this case, extension of the rod will be calculated. Do we calculate self weight also? Due to self weight also? If we have to calculate extension due to self weight also, so there should be density should be given. Okay, but density is not given in the question. So when density is not given in the question, we will not consider elongation by self weight. We have to consider elongation by load only. So elongation by load P will be equal to how much? 4PL upon pi D1 D2 E. Now 4 into P. Load, how much load? Load is 12 kilonewton. So 12 into 10 to the power 3. And what is the length? 400 mm. 400 divided by pi D1. What is the value of D1? D1 is 24. D2 is 12 into E. Young's modulus is given as 2 into 10 to the power 5. 2 into 10 to the power 5. Okay. So now let us see what are the terms that will be cancelled out. So 12 and 12 will cancel out. Okay. Here there are 5 zeros. 5 zeros cancel out. 4 into 4, 16. 4, 6 are 24. 4, 2, 2, 2, 3. Okay. So what is remaining? So we are left with 1 by 3 pi. We are left with 1 by 3 pi. So correct answer will be option D, 1 upon 3 pi. So most of the times in ESE, what will happen? You will be given values such that most of the things will be cancelled out with each other. Okay. So ultimately small values will be remaining. So here 1 upon 3 pi is the correct answer. Let's move on to next question. Poisson's ratio of a material is 0.3. Okay. Then ratio of Young's modulus to bulk modulus. So ratio of Young's modulus to bulk modulus. So Young's modulus is equal to 3K 1 minus 2 mu. So E upon K will be equal to 3 into 1 minus 2 mu. This is the ratio of Young's modulus to bulk modulus. So 3 into 1 minus 2 into mu. Mu value is 0.3. Okay. So 3 into 1 minus 0.6. So 3 into 0.4. 3 into 0.4 is 1.2. So E by K is equal to 1.2. Correct answer is option C. So relationship between elastic constants is very important. Okay. Many questions are asked from the relationships between elastic constants. Okay. Next question. Again, you see relationship between elastic constant. Okay. So the relationship between Young's modulus E, modulus of rigidity C, and bulk modulus K in an elastic material is given by. So that relationship we know, but we usually represent modulus of rigidity as G. Okay. So 9 kg upon 3k plus G. This is the relationship. Okay. So according to the notations given in this question, we will be getting 9kc upon 3k plus C. 9kc upon 3k plus C. Correct answer will be option A. Option A is the correct answer. Next question. Yes, very good, Mech Zone. Correct answer will be yes. For other branches also it is very useful. Okay. Similar questions are there. Now, which of the following statements are correct? So ESE 2013, this was very good theoretical question. Okay, multiple statement question. Listen carefully, see carefully. Okay, in a ductile material, elastic deformation is more predominant than plastic one. Is it correct? In a ductile material, what do we mean by ductile material? In ductile material, plastic deformation is much higher than elastic deformation. Yes or no? Elastic deformation range is this much only. This is elastic deformation range, and plastic deformation range is this much. Okay, so this first statement is wrong. In a ductile material, elastic deformation is more predominant. No, plastic deformation is more predominant. So first statement is wrong. Okay, now let's have a look at the second statement. Second statement, brittleness is not an absolute property of a material. Brittleness is not an absolute property of the material. See, if a material, if I take mild steel at normal temperature, this is ductile. At normal temperature, mild steel is ductile. If I freeze it, okay, let us say minus 24 degrees Celsius, and when I apply load, this will become brittle. So brittleness is not absolute property. Mild steel at normal temperature is ductile, and at very low temperature it will become brittle also. Okay, so it is not an absolute property of the material, and it also depends on the rate of loading. If I apply sudden loading, then it might happen that mild steel will break without undergoing such elongation. Okay, so it is not an absolute property of the material. This statement is correct. Okay, then rate of loading has no influence in changing the behavior of a material from ductile to brittle at low temperatures. This is also wrong. At low temperatures, rate of loading will have influence. Okay, if I apply loading suddenly, what will happen? It will break. But if I apply loading slowly and slowly and slowly and slowly, what will happen? It will keep on elongating. Okay, so it will be brittle. So it has no influence. No, it will have influence. So this is also this third statement is wrong. Next, fourth statement, under hydrostatic compression, a brittle metal may change into a ductile one. Okay, now if I take a brittle material and not apply hydrostatic loading, I am applying axial loading like this. Okay, so it will fail in shear like this. It will fail in shear like this. Okay, so this brittle material will fail in shear if it is not hydrostatic loading. But if on the same material, if I apply hydrostatic loading, in hydrostatic loading, what will happen? Loading is provided on all the sides and same value of loading. Now can you tell me where you will get maximum shear stress? There is no plane of shear stress. No shear stress will be there. There is no shear stress. When there is no shear stress, the failure will not happen according to shear. It will undergo deformation. Okay, but there is no shear plane, so shear deformation, shear failure will not happen. So it will fail just like a ductile material. Okay, so under hydrostatic compression, brittle metal may change into a ductile one. This is correct. Okay, the failure pattern will change and it will behave like a ductile metal. Okay, so 2 and 4 are correct options. So correct answer is option D. Is it clear to all of you? Is it clear? Any doubt in this? Okay, so I hope this question is clear. Let's move on to the next question. Okay, so next question, if the Poisson's ratio for a material is 0.5, so mu is given as 0.5, then the elastic modulus of the material is. So elastic modulus, Young's modulus. Okay, so we have to find relation between Young's modulus and shear modulus. Okay, so how many times it will become of shear modulus. Okay, so E is equal to 2G 1 plus mu. See, you can see how much important are the relationship between elastic constants. Okay, so you have to remember the relationship between elastic constant. Okay, so Poisson's ratio, let us put 0.5. So this will be 1.5, 1.5 into 2, it will be 3. So Young's modulus will be 3 times the shear modulus. So correct answer will be option A. Option A is correct answer. Clear? Let's move on to next question. Yes, correct. Mechanical zone. Next question, a metal bar of 10 mm diameter when subjected to a pull of 23.5 kilonewton gave an elongation of 0.3 mm on a gauge length of 200 mm. Okay, the Young's modulus of elasticity of the metal will nearly be. So now just try yourself. First try yourself and then I'll solve it. Okay, so let me, till then you are solving, let me write down the given information. So diameter is 10 mm, pull force is 23.5 kilonewton, elongation, change in length, delta will be equal to 0.3 mm, gauge length 200 mm. So we are asked E. So Young's modulus, so delta is equal to PL upon AE. We know the formula, delta is equal to PL upon AE. So from here we can calculate, we can find E. So Young's modulus will be equal to PL upon A delta. Okay, so E will be equal to P. What is the force? 23.5 kilonewton. So 23.5. Here kilonewton per mm square. So we'll put all the values in either kilonewton or mm. Okay, so force values will be writing in kilonewton only, no need to convert. So P, length is how much? 200 mm. 200 upon A, pi by 4 into d square, that means 10 square, into delta is delta change in length 0.3 mm, 0.3. Okay, so let us see what we will be getting. So 23.5 into 200 into 4 whole upon pi into 100 into 0.3, pi into 100 into 0.3, that means 30. We will be getting 199.47, 199.474 kilonewton per mm square. Okay, so approximately this is equal to 200 kilonewton per mm square. Okay, so 200 kilonewton per mm square, option A will be the correct answer. Correct answer will be option A. Let's move on to next question. A steel rod 2 meter in length, 40 mm in diameter is subjected to a pull of 70 kilonewton as shown in the figure. Okay, so axial force applied is 70 kilonewton. Axial force applied is 70 kilonewton. Length is 2 meter. To what length should the bar be bored centrally? What do we mean by boring of the bar? We'll bore it like this centrally. We'll make it hollow. Okay, like this. So to what length? Let us say we have bored it to x length. Up to x length we have made it hollow. Okay, from one end, so that total extension will increase by 20% under the same force. The bore diameter is 25 mm and Young's modulus is this. Okay, so original diameter is 40 mm. Okay, then this diameter, board diameter, is 25 mm, and now we have to find out the length to which it is bored. This is very good question. Okay, very good question. Do you want to try yourself? Okay, let me solve it. So before boring, in the solid bar, initially delta I, okay, so change in length of the bar initially will be equal to PL upon AE, PL upon AE. Okay, so force is how much? Force is 70 kilonewton. So 70 into 10 to the power 3 is the force. Length, we will take total length 2 meter. 2 divided by A. Area will be taking this corresponding to this 40 mm diameter. Okay, so pi by 4 into 40 square into Young's modulus. Let us keep Young's modulus as E only. Okay, so this is the initial before boring, when it was not bored. Now after boring, what will happen? We'll have to consider two parts, elongation of this part and elongation of this part separately, and elongation of both the parts will be added to get the total elongation. Okay, so this part elongation plus this part's elongation, both the parts elongation will be added. Okay, so length of this part is x and this part's length will be 2 minus x. 2 minus x, this part's length will be 2 minus x. Okay, so finally delta final F, it will be P into L1 upon A1E plus P L2 upon A. Okay, so this part, second part, area is same as before, no change in area. Okay, but here area has changed. So what is the value of force? Force is P, same. Okay, so 70 into 10 to the power 3 into L1. What is the length L1? This is x divided by A1. It will be pi by 4 into 40 square minus 25 square. Okay, so after boring, central boring of 25 mm diameter, cross sectional area will remain as pi by 4 outer diameter square minus inner diameter square. So pi by 4, 40 square minus 25 square into Young's modulus plus P, again it will be 70 into 10 to the power 3 into length L2. Here length L2 will be 2 minus x, so it will be 2 minus x divided by pi by 4. Now in this part we are having original area pi by 4 into 40 square into Young's modulus E. Okay, now in the question we are given that after boring total extension is increased by 20%. So that means delta final will be equal to 1.2 times of initial extension. Okay, so that means let us put these values, 70 into 10 to the power 3 divided by pi by 4 into E. I think this will come common in both the parts. 70 into 10 to the power 3, 70 into 10 to the power 3, this will come common. Pi by 4, pi by 4, pi by 4, common. E is common. Okay, what is remaining here? It is x upon 40 square minus 25 square plus 2 minus x upon 40 square. Okay, that will be equal to 1.2 times into delta initial. So delta initial is 70 into 10 to the power 3 divided by into 2 divided by pi by 4 into 40 square, pi by 4 into 40 square into E. Okay, so let us cancel out whatever things we can cancel. So 70 into 10 to the power 3 cancelled out, pi by 4 cancelled out, and Young's modulus cancelled out, Young's modulus cancelled out. Okay, so what is remaining? The remaining part is x upon 40 square minus 25 square. So let us calculate what is the value of 40 square minus 25 square. 40 square minus 25 square, 975. So x upon 975 plus 2 minus x upon 1600, that will be equal to 1.2 into 2, that means 2.4 upon 1600. So we have to solve this. Okay, so we can multiply 1600 to everything. So 1600 divided by 975 will be getting 64 by 39. So 64 by 39x plus 2 minus x is equal to 2.4. Okay, so this 2 minus x, 2 will go there, it will be remaining 0.4. Let us add one more slide. Now let us see what we are getting. So 64 by 39x minus x. So 64 minus 39, 64 minus 39, 25. So we'll be left with 25 by 39x. 25 by 39x will be equal to 0.4. 0.4. So x will be equal to 0.4 into 39 by 25. So 0.4 into 39 by 25 will be getting 0.624. 0.624. So x will be equal to 0.624. So up to this length we have to bore this centrally, so that now under the same load we will be getting 20% more extension. Okay, the extension is increasing by 20%. Okay, so 0.625 was the answer, 0.624. Okay, 0.624. So correct answer will be option D. This is the closest answer. Okay, clear? Let's move on to the next question. Next question, a member A, B, C, D. So ESE 2014 questions we are solving now. Okay, A, B, C, D. Subjected to a force system as shown in the figure. So this is the force system. Resistive force in part BC. So what is the resistive force in part BC? Resistive force in part BC, either we can do summation of all the forces towards the right, or we can do summation of all the forces towards the left of this section. Okay, now from both the sides we will be getting same answer. Okay, so let us see. 45 is away from the section, it is giving tensile. 365 is towards the section, that is giving compressive. Okay, so if we check here, 45 is tensile, so positive, minus 365, because why minus against 365? Because it is compressive. Okay, so we will be getting minus 320. So minus 320 here, minus is indicating that compression is there. Okay, so from this side if we calculate, we are getting minus 320, that means 320 kilonewton compressive force. Now if we sum these two forces, what we will be getting? Here 450 is towards the section, that means it is compressive, so minus 450, and 130 is away from the section, so plus 130. So minus 450 plus 130, again we will be getting minus 320. So what does this minus indicate? Minus indicate compressive. Okay, so from both the sides we will be getting same answer. You can calculate from either of the side. So minus 320, that means 320 compressive. Correct answer will be option D. Clear? Let's move on to next question. Two-dimensional stress system on a block made of a material with Poisson's ratio of 0.3. So Poisson's ratio is given here 0.3. Okay, so this two-dimensional block is given here. Here in the x direction, let us say this is x direction, and let us say this is y direction. So in x direction, sigma is given as 60 Newton per mm square. That means sigma x is 60 Newton per mm square. This is sigma x, and sigma y is not known. Sigma y is sigma. Okay, so the limiting magnitude of the stress sigma, so as to result in no change in length AB. There is no change in length AB. Length AB should remain same. No change in length of AB. That means there is no longitudinal strain in x direction. Okay, so strain in x direction should be 0. Okay, so condition here is that strain in x direction is 0. So strain in x direction, we should use generalized Hooke's law. Okay, generalized Hooke's law. Sigma x upon E minus mu sigma y upon E minus mu sigma z upon E. So since this is a two-dimensional stress system, this will be 0, and sigma x is given as 60 Newton per mm square, and this is away from the section, this is tensile, so it is 60 divided by E. Young's modulus given? Not given? No need also. Young's modulus is not required also. Minus mu, Poisson's ratio is 0.3 into sigma y, here it is also tensile, the value is sigma, so this is E, it is equal to 0. So E and E will come common, and multiplied by this it will cancel out. So 0 will be equal to 60 minus 0.3 sigma. So sigma will be equal to 60 by 0.3. So we'll be getting 600 by 3, that means 200 Newton per mm square. What was the unit? Yes, Newton per mm square. 200 Newton per mm square. Correct answer will be 200 Newton per mm square. 200 Newton per mm square. Correct answer will be option C. So option C is the correct answer. I hope you got it. Clear? Let's move on to next question. The symmetry of the stress tensor at a point in a body when at equilibrium is obtained from. Symmetry of stress tensor, okay, when at equilibrium. So symmetry at stress tensor will be symmetrical when tau xy will be equal to tau yx. Tau xy will be equal to tau yx. Okay, so symmetry of stress tensor is coming from this condition, tau xy is equal to tau yx. Now this condition is satisfied, this condition will hold true corresponding to moment equilibrium equations. About this point, if we take moment of this, and about this point we take moment of this, and if we in equilibrium, moment equilibrium, these two will become equal. So it is corresponding to moment equilibrium equations. So option C will be the correct answer. Clear? Next question. Statement 1. There are two independent elastic constants for an isotropic material. Yes, this statement is correct. Independent elastic constants are 2. Although total number of elastic constants are 4, E, mu, K and G. But they are not independent. Independent are 2 only. Okay, they are all are related to each other. All metals at micro level are isotropic. If we go to micro level, that means this is steel, let us say. So steel, we say that it is isotropic. But when we go at the micro level, what we will find, here it is iron, here it is, you know, carbon atom, and micro level, if we go at the micro level, we will see that properties will differ in different directions. Okay, so at microscopic level, if we go then all metals will be non-isotropic, everything will be non-isotropic. Okay, if we go to microscopic level, so this statement is false. This statement is false. Okay, so at micro level they will be non-isotropic. Okay, so statement 1 is true, but statement 2 is false. Correct answer will be option C. Option C will be the correct answer. Clear? Next question. The failure surface of a standard cast iron specimen. So cast iron is brittle material. Brittle material. Okay, so cast iron specimen of circular cross section subjected to torsion is on helicoidal surface at 45 degree. Yes, so if cast iron brittle material is subjected to torsion like this, okay, it will be subjected to, the failure will be something like this. Okay, at 45 degree, rough helicoidal surface will be formed at 45 degree to the axis. So this is true. True, this is correct. Statement 2, the failure occurs on a plane of the specimen subjected to maximum tensile stress. Yes, at this plane we will be getting maximum tensile stress like this. Tensile stresses will be there, maximum tensile stress like this. Okay, so maximum tensile stress, and cast iron is weak in tension. So correct, this is also correct, this is also true, and it is correct explanation also. This is also true and it is explaining it also. Okay, so that means option A is correct. Both statement 1 and statement 2 are individually true, and statement 2 is the correct explanation of statement 1. Okay, option A is correct. Let's move on to next question. Okay, so these were all the questions from ESE 2007 to ESE 2014. Okay, so today we have discussed ESE prelims questions of chapter 1 of 8 years. Okay, so classes will be every, let me give you the timetable. Classes will be every Tuesday, Thursday, every Tuesday, Thursday and Saturday. Classes will be every Tuesday, Thursday and Saturday, 9 PM to approximately 10:30 PM. Okay, 9 PM to approximately 10:30 PM will be the classes every Tuesday, Thursday and Saturday. Okay, so I hope you enjoyed the session. Okay, so all the previous year's questions of EAC prelims will be completed from 1995 to 2023 of all the chapters. So all the chapters one by one we will pick all the chapters, and for all the chapters from EAC 1995 to EAC 2023 in this series. Okay, so be there, and these questions will help you in both the examination, in GATE examination as well as in EAC examination. Okay, so I hope you enjoyed today's class. We'll see you in the next class on Tuesday. Okay, so next class will be on Tuesday. We'll see you at that time. Bye bye. Take care.